issues of zeros in the table and what to do about zeros. This piece of chalk is not right. What to do with zeros. I'm just going to wrap that up today. So we had several approaches. Merge cells. And this is kind of one of the best. So if you can justify merging cells, it's in some ways the best possible response because you haven't done any heroics. You haven't had to change your model, or, you know. So if you can merge cells and you're comfortable merging cells, that's often the best way to get it. But that doesn't always work. And of course, you have to watch out for Simpson's paradox. We could regularize. And that means that a lot of the problems from zeros are created by choosing parameters that maximize the log likelihood function. If we adjust that log likelihood function with some penalty that typically that associated to a norm of a way of measuring the size of this vector, that will push all of our parameter vectors towards some desired sort of smoothing situation. So it'll push them all towards 0 or toward 1, depending on how you think about it. And that is one way to prevent the blow-up that happens. So we had kind of and we think about regularizing as also sort of being like a cheap Bayesian. So a even better way would be to be full Bayesian, but that's often too complicated to do for it might be computationally difficult. We had an even cheaper version, which is related to these two, which is to add, 1/2 or something similar to cells, or some small value to cells. And that's kind of like, if even regularization is too onerous, that's kind of a quick and dirty version that will also tend to smooth things toward having 0 parameters, right? Because if we added, in the limit, if we added a lot to all the cells, we would just get a uniform distribution. Right? So in both of these cases, we're kind of shrinking, pulling the model toward the uniform distribution in order to get rid of excessive dependence on the data. Usually, the excessive dependence on the data is not a huge deal, but when there's zeros in the table, that can cause big problems. Similar to the situation where early on when we were doing the confidence intervals, and sometimes, our confidence interval construction for flipping a coin doesn't work well near 0 or near 1. And one of the main reasons it doesn't is because if you happen to get 0 successes, your confidence interval becomes degenerate, and it never captures the reality. And so similarly, in the off chance that you're doing this discrete thing and you get zeros in your table by chance, a lot of the sort of statistical asymptotic behavior falls apart. And so we're trying various ways to correct for that kind of excessive dependence on the data. We can add constants to cells. The fourth thing we could do was to change the model. And in some ways, this is like merging the cells, which is changing the model, but this is even more opinionated in the sense that what we're doing here is typically making the zeros structural, what's called structural zeros. That is, we're taking zeros that we've observed and saying, you know what, we're going to assume that these cells are actually never seen, and that we can treat them as though they were impossible. And that's a pretty strong assumption. Obviously, it changes a lot, including your degrees of freedom. And sometimes it can make sense to do. So I'd say that this is sort of harder to justify. These are maybe increasingly difficult to justify, or require increasing amounts of text devoted to explaining why it is that it was okay that you did that.
Okay, well, can you do it if the event is extremely rare and it's not really what you're interested in?
Can you do the structural zero thing? Yeah, I think that's probably okay. If you know that it's extremely rare, So even the example I gave, right, of like prostate and ovarian cancer, it's conceivable that those zeros are not really 0, and that there's a sufficient chain of mutations or whatever that could happen, right? So That's probably, yeah, I mean, in the physical universe, zeros are hard to ever obtain for absolute certainty.
Yeah.
Yeah.
It's all wondering, so the data structure we here is whether it's saying there are a lot of, it kind of the sparse, the matrix, right? Say there are a lot of, the zero element is more than the non-zero element, right?
That's right. When you have too many, sometimes this this kind of regime is written as the shorthand is this, and this means number of states is much larger than the number of observations, and in which case you have lots of cells that are empty. Sometimes some other letter for P, but and that's usually this is in the context of the sort of regularization approach, but it applies in all these situations. And the last thing I want to mention, which isn't really in itself a technique, but because it's not an adjustment to the model, but let's say what it is anyway, which is a trick that we've seen before, which is that put the emphasis of your analysis, say your goodness of fit statistic, so this doesn't help with our parameter estimation, but one of the things that falls apart in this too many zeros situation is the chi-squared approximation. So one of the things that we can do is to focus instead on comparing different submodels rather than judging the overall g-squared or the overall likelihood ratio or Pearson test. So what do we mean by that? Well, the idea is that, remember, we're looking at these maximal sufficient statistics, maybe minimal sufficient statistics. Anyway, the facets, the biggest things that we're measuring, the largest interaction terms. Right, that's what our model is made of. This is a hierarchical model. So I have something like log mu equals a global plus some local, some terms for main effects, and then I have some interaction terms. Say this would be what model would this be that I just wrote? We have a name for that particular type of model. Log linear model, but specifically among the choices of log linear models, there's 9 log linear models, as you did in the midterm, on 3 variables. So which one is this? Yeah, Poisson. Yeah, this is a Poisson log linear model, right? And if I don't estimate this, if I can think of it as I can factor out the global Poisson and think of it as multinomial. But what I'm looking for is which dependent structure do I have in mind here?
A conditional.
Yeah, that's right. This is a conditional independence model. This is the model AB, BC. Whereas a graphical model, which maybe we'll talk about towards the end of today or next time, ABC. Or if I want to sort of draw in these factors, A, B, C. And the sufficient statistics, the largest sufficient statistics are the interaction terms. So we want to focus the analysis on these. These correspond to the overlap between these two variables. These are kind of the largest subtables of counts that we're measuring when we're looking at the table. And the idea is that if I focus on comparing models, like saying this one versus ABC, the one with no BC interaction, then really the only thing that I'm paying attention to is how many times each of the combinations of the variable BC happens. And if none of the entries in that subtable, that marginal subtable, have zeros, I'm closer to okay, right? So let's say the approximation is closer to chi-squared or normal if then the individual cell count, or let's say for these sufficient statistics, then for the individual cell counts. In other words, I could have zeros in my table for individual cell counts, but still have, and that would cause problems with my chi-squared or my other asymptotics, but I could still, with respect to these other statistics that I'm actually looking at, not have zeros, and that wouldn't cause a problem. And that makes sense, right? Because suppose I have any table where my approximation works well, and I start measuring more things. Of course, I'm going to end up with a table with lots of zeros. When I've marginalized those out, the chi-squared approximation works fine, right? So in some sense, we're always in this situation, right? There's always factors that we're ignoring, and we're hoping that all the things we ignore average out to be normal or to be chi-squared. So as long as we only focus on those things where there's no zeros, which is often the case when we're comparing two models, like this model inside this model, inside of AB, BC, then we can rely on that same kind of approximation working. Okay. So we have this rule of thumb for g squared that was when the degree of freedom is greater than 1, it's okay to have less than 20% of cells with mu hat less than 5. And for delta g squared, we have a rule of thumb which is similar. These things can be small, the estimated cell counts, but if the sufficient marginals, the ones we're actually looking at, are mostly more than 5, then we should be okay. That's a rule of thumb. And in some sense, this is the same rule of thumb we've already used, right? In the sense, if we imagine that the real data had lots of other categorical factors that we marginalized over simply because we didn't measure them. And then whatever you do, whatever method you choose, of course, you should do some sensitivity analysis, try different techniques, move data points around a little bit, and see whether you get an answer which is drastically different. Yeah.
Sufficient marginals. What's the next word?
Mostly. Oh, so if the sufficient marginals are mostly 5 and more, we should be okay. Are mostly. Here, let's do this. If most sufficient marginals are greater than or equal to 5. Is that clear? Yes. And there's another sort of rule of thumb, which is that when you really do have a small, sparse table, small n and sparse, the Pearson tends to be a bit better. I usually like likelihood, but it's easier to interpret, but it tends to be a little bit better. Okay. So this depends. So that's all I want to say right now about sampling zeros and structural zeros, and we may get back to it when we talk about missing data later on. What I'd like to discuss now is to continue with our sort of lesson 10 linear models, log linear models. We've explained it a couple of different ways, and I'm going to explain some other aspects of it, or another way of looking at it today. I don't want to be redundant, but I think that This is kind of what this class is about, and I want to give you a bunch of different points of view on it. So today's point of view is a little bit more thinking about what this means in terms of the constraints that we're placing and what distribution we choose subject to those constraints. Okay, so remember that we're interested in these sufficient statistics. We're measuring about the model that correspond to which of these parameters are in there. And we can think about this in terms of a matrix, where on the top we have 0, 0, 1, 0, etc. These are, I can think of them as counts in the contingency table. Right. You can also write n for that if you would like. Or we could think about there being probabilities that we estimate. Probabilities, right? There's maybe some true probabilities that come from the model. There are estimated probabilities. That come from the, this is the truth, this is the estimated probabilities after we fit the MLE, and there's also the empirical probabilities, which is just the counts divided by the sample size. Right? So those are our columns, and then our rows are labeled by our parameters. A global parameter is the first variable 0, is the second variable 0, and so on. Right? And interaction terms that we want to include in the model. And these sort of these rows index the sufficient statistics, or the subsets in our hierarchical model that we're counting. So this is 1, these are all 1s. This will be 1, 0, 1. This would be 0, 1, 1, 0, and so on. Right? So when we think about this matrix, we could say that the jth column, so the rows I can interpret as sufficient statistics, or what I'm measuring, or in terms of the parameters. The columns is the log of a monomial expression. Monomial is just a bunch of variables multiplied together. I can think of it as a log of a monomial that represents or is proportional to the probability of this. If I don't have a lambda global one, then it's just proportional. If I do have that, then I can say that it's a probability or it's an expected count. So there's a little something which I tend to gloss over, which is that whether I sort of force these to be probabilities or whether I get out counts, and whether or not I multiply by the global total. Hopefully that's not too confusing. Okay. So in other words, what are these things? This is exp, lambda plus lambda 0x. If there was a 0 in the first place, and maybe if there's no more zeros, then it's just main effects. It might be that, right? So that might be the one that corresponds to P 0, P1, 1, 0, right? If I have only main effects and no interaction terms. And I can think about this as being some theta, where each theta I is equal to exp of lambda I, if I think about all of these parameters being exponentiated, raised to the power of that column. So it's a vector. So this is a vector, and this is a vector. I'm just multiplying them together. Theta I, Aij. It's just a notation for this. And then the log linear model has a set of probability distributions. So I'm not interested in the overall count, just the multinomial part, is the image of the orthant, the positive orthant. So I could think about, I have sort of a parameter space exponentiated, not the log parameter space, which is real numbers, positive real numbers, strictly positive real numbers. This is just e to the each of these things and that I multiply together in order to get a probability. And then I have applied some map, which is described by this table A. Let's call it F, that goes from RD, or theta, positive part, to Rm, where this is the number of cells, right? Which gives me, for each choice of parameters, it gives me a probability distribution. It gives me a model. I can write that as theta goes to the sum over all of these. So if I'm not interested in the overall count, I want to normalize it so everything sums to 1. Theta A1, theta AM. And this, alternately, I can think of as absorbed into the lambda. It's just a normalizing constant. Yeah.
So I kind of lost the implementation of the H. So H is not here, it's not here with the space, right?
Oh, it's not H, this is capital theta. Yeah. Unfortunate coincidence of linguistic coincidence, but capital theta looks like an H with a circle around it. Yeah. You can ignore that and just think about this if you like. Okay, so since we're interested in the multinomial case, as opposed to the Poisson, right, we have this normalizing constant, and it's true that this map, whatever it is, that sends parameters to probability distributions, right? It ends up in this space Rm of, well, really probability distributions, or it really ends up in the simplex, m-1 simplex. But if I take the input vector and I scale it by something, because I've divided here, it doesn't change what I get. Okay. That only can do, the scaling is like changing the global rate, and that's not, from the multinomial point of view, that's not important. So that doesn't change anything. And this is kind of why we have that thing where the dimension drops by 1. So I said that the degrees of freedom is equal to the number of lambdas, except that if we're in the multinomial case, we have to ignore one of the lambdas. And that's where it goes, so because that scaling doesn't affect the probability distribution for the multinomial. So the dimension of the image is the rank of this matrix minus 1 in the multinomial case, or just the rank of the matrix in the Poisson case. So now what we want to do is maximum likelihood estimation. So maximum likelihood estimation for this model proceeds as follows. So we're given cell counts, call them U1 up to UM. So these are how many observations we saw in each cell. And we maximize a likelihood function P1 to the U1, P2 to the U2, which is the probability of each thing raised to the power of the number of times it happens, PM to the UM. And that maximization problem is subject to that this vector of probabilities lies in the model. Right, so this is just the same picture. I have some data point U, I divide it by the total observations. I have a model, which is a set of all allowed probability distributions, and I want to pick the point on this that is sort of closest to this in some sense. That's the KL sense, but it maximizes this function. This is the maximum likelihood idea. And if we write that function out, we rewrite this function a little bit in terms of our parameters, our exponentiated versions of our parameters, the thetas rather than the lambdas. We get something that looks like this. We want to maximize this vector of thetas to the power of the matrix A times the vector. So this is a vector, this is a vector. So I'm using this this type of multi-index notation, I have this vector, it's raised to the power of a times u. So this is a product of thetas, each of which is an exponential, right? Product of thetas, like theta xy 0, 1, where theta xy 0, 1 is just exp lambda 0, 1 xy in the other notation. Okay? And it's subject to, well, okay, our theta is just in RD now. That's not very restricted at all. Each theta has to be the exp of something, so it has to just be a number bigger than 0. And we'd like them all to sum to 1, since we're thinking about multinomial case. And that would be how we write that sum to 1. So that's a slightly simpler thing, right? So this constrained optimization problem is not clear how to solve because we have to get a handle on this thing. This is another constrained optimization problem, but the constraint is much simpler. I have an orthant, and then I have like just a single constraint. And just to be absolutely explicit, let's say AU, the theta to the AU, I can write it out as the product I equals 1 to D, the product J equals 1 to M, theta I, Aij, Ui. Okay. So such a thing is called an exponential family. Because we're exponentiating a lambda dot producted with this AU. Okay. So what does this say? What's the point of this? One of the points is that this means that the likelihood depends on the data only, the data u, only through this function AU. Okay? Only through AU. Which is what I mean when I say, okay, A computes the sufficient statistics. Once you know A of u, and you can call this a vector B. B is the vector of counts. How many times did x1 occur? How many times did x2 occur? How many times did x equal 0 and y equal 1 at the same time, and so on. That's what this vector looks like. It only depends on that, and this is called the vector of sufficient statistics, or just the sufficient statistics. And A is called this, sometimes just called the sufficient statistics also, confusingly. I like to call it the sufficient statistics matrix. So it's the thing that computes the sufficient statistic from the data. And what's special about this whole class of models is that A is linear. Right? A is just, this is a linear function. The sufficient statistics are a linear function of the data. And that's what makes them log linear, and that's kind of where all of the niceness, if you believe it to be nice, that happens in this comes from. That's a strong assumption, but it's a useful one. Okay, so we can think about our maximum likelihood problem as maximizing this theta to the B, which is AU, subject to that theta is just some positive numbers. Are greater than or equal to 0, greater than 0D. Or I can think about that as lambda is just some number, a vector of lambdas. And this sum to 1 condition holds. And I can always increase my scores by sending the thetas off to infinity, but that's not, we need to normalize by that. Okay. So set up this way, I'm going to give you a couple of facts or propositions. We haven't had a lot of propositions in this class, and I'm not going to go through the proof or anything. Well, I mean, sketch the idea, but let's just explain what's going on. Okay, so proposition, so fix the matrix of sufficient statistics, A, the matrix which computes sufficient statistics, and fix the count. Theta for the cells. U, U1 up to UM. These are counts. And so our sample size, we'll call it big N, U1 plus UM. Okay. The sufficient statistic from the data of the data is AU. Call it B. And let P hat be F of my estimated thetas after I solve my maximum likelihood, be the estimated cell probabilities, expected cell probabilities. Ideally, I'd like this to be at an MLE, but let's just say at the MLE. In fact, it's true at also just like a local maxima, but let's say at the maximum for the likelihood problem, the maximum likelihood problem, which was max P1 to the U1 times P2 to the U2 times up to Pm to the UM, and subject to this P by being in the model, being an allowed distribution from our assumptions. And the conclusion is that I take this matrix A and I multiply it by the estimate. Now I'm plugging in the estimated probabilities into A instead of U. That's equal to 1 over the sample size times the sufficient statistic, B. Right? So what does that say? It says that at the maximum likelihood estimate for this type of model, the sufficient statistics and the estimated probability distribution match exactly. We've chosen a probability distribution. This maximum likelihood procedure mysteriously chooses a probability distribution, and that exactly matches what we would get if we just said, give me a probability distribution that matches all of the measurables, right? Now, it's not the only probability distribution that solves this problem. Right? I could add anything in the kernel of A, for example, and I would get another probability distribution. If it was still a probability distribution, I could add things to this and get something else that solves this problem. So generally, there's a lot of them. There's a lot of P's that solve this problem, that match all of these things. And we have to choose among those P's. And this model uses a particular method for choosing among those P's. So here's the picture that you should have in mind. So we have, we have U, we have AU equals B, and we would like all of the P's. We're interested in the set P such that AP equals B, right? Such that 1 over n, sorry. Such that the sufficient statistics match exactly. You do that, generally this is going to be some kind of polytope, some big high-dimensional polytope. And among all of the points that are feasible, that satisfy this constraint, we have to choose a point that we like. So any guess as to how we choose that point, or what's a principle for choosing that point? If we forget about maximum likelihood, we just said, okay, I want to match this, there's a whole set of things that match. Which probability distribution is most attractive among those? Or any principle for choosing one. Think about that for a minute. We'll come back to it. So let me explain a little bit about why this statement is true. AP equals 1 over NB. So a local max of the ML problem, maximum likelihood problem, is a critical point. Right, when we're doing calculus, we're doing a maximization of theta to the b plus lambda, different lambda, sort of, not really different, but sort of different, j equals 1 to m theta aj. So what's this? This is a Lagrange multiplier problem. Remember from calculus. I want to do a constrained optimization. I have a simple linear constraint, and I have this function. And, well, it's not linear because of this, but and I just say it's a critical point. Find the critical points of the thing I can freely change, and then I put in a constraint. I put a Lagrange multiplier. So I get an extra variable. It's just this optimization technique. And this is the probability sum to one constraint. So we have now theta 1 up to theta d, and also lambda as unknowns. So there's some calculations that you can do, which I won't go over the detail of, but the idea is you take a scaled gradient theta 1 d theta 1 up to theta m d theta d, and consider the critical points of the scaled gradient of this, and you get the result. Okay, so that, anyway, it's just the idea of why that's true. And then we want to think about this problem of, okay, I have a set of feasible probability distributions in that picture. So given A, my matrix of sufficient statistics, and my scale D, my vector of sufficient statistics, we have a set of scaled sufficient statistics, i.e. probability distributions, scaled counts, say, distributions which match the sufficient statistic. That's this P, some polytope, some set of vectors in our M such that A, P is equal to 1 over N B. And let's make these all greater than 0. Okay. So it's not really, I lied a little bit, it's not really a polytope in the sense that I'm going to require it to be just the interior, they're relatively open. So I require these to be all positive, but if you close it, you'd get a polytope. Okay, so then the question is which point in this feasible set should we choose? And any ideas? So any ideas for which one that is? Well, even a principle or an idea for choosing that. So I say, okay, I have a family of probability distributions. These are all perfectly valid answers from in the sense of matching the sufficient statistic. Which distribution would you choose if you just had to choose one? Normal. Well, normal is not a choice because these are discrete distributions. Yeah. We want something that's the nicest somehow, right? Well, no. So these are just vectors. These are just vectors like, 0.2, 0.3, 0.4, 0.1. Right? Vectors like that, for example. If m is equal to 4. We have a bunch of these things. We have a four-dimensional set of these. And we want to choose one of these vectors. So it has to be something about these vectors that satisfy these constraints, that I can choose a vector like this versus some other numerical vector. I don't know. 0.25. Suppose this was two things that were in the, suppose these two were both in the feasible set. I said both of these match the marginals. Which one would you choose?
Second.
Why?
No, it's easy.
It's easier. You quantify that?
Like all the probabilities are equal.
Yeah, they're equal. Okay, so what if it was like, here's one, let's see if I have 0.3, let's make it, I don't know, 0.26, 0.26, 0.26, and then I have to do, so 0.22. So what if I didn't give you that one? Which of these would you choose? You'd probably still choose this one, right?
Yes,
Right.
but I don't know why.
You don't know why. Okay. So here's two ways to think about it. One is, well, we should choose something, the one which is somehow closer to the uniform distribution. Okay? That's what you were choosing. So that's one idea. And another idea is that we should maximize ignorance. That is, we have a set of feasible things, feasible probability distributions. We should choose one that somehow reflects the least assumption about the data. Right? It maximizes how little we know. And so there's a concept that matches this pretty well, which is the concept of entropy. So every probability distribution has an entropy, which is like the entropy in the sense of Shannon. It's related to how much it would take to encode a sequence of these things, related to many other things. And so one of the solutions is to say, well, of all of the points that are feasible, I'm going to choose the point which has the maximum entropy. And it turns out if you choose the right notion of closer to uniform, that is in terms of KL divergence, these are the same. Okay? So the one which gives me reflects the most ignorance, that is, I express the least information about the experiment, or I have the least information given the probability distribution in the sense of entropy, and is close to the uniform distribution in the sense of KL divergence, which is our measure of how close probability distributions are. Either of those answers will give the same answer. So that's the answer. You choose the point which is the maximum entropy point, and magically, that is exactly the point. I have this space of feasible things. I have another space here of the model. These two sets intersect at one point, and that point is the maximum entropy point. So that gives you sort of a independent, if you didn't know anything about likelihood, you didn't believe likelihood, this gives you an independent way of coming up with the same model. Right? You just say, give me a probability distribution which matches all of the marginals, or all of the sufficient statistics, and which maximizes my ignorance. And that gives you the same answer. Okay, so this theorem, this result, is called Birch's theorem in statistics. So last semester I taught a class in algebraic geometry, and I think we called it the moment map for toric varieties, which is another name for the same result. So we fix A, our sufficient statistics matrix. We fix our data matrix, our data vector of counts, natural numbers, strictly positive, and we let B equals AU be our vector of sufficient statistics. Then the probability, or not the probability, this polytope PA of B of feasible points. This is PA of B, and this is F of RD. I intersect that with F, all the points on my model, is 1 point. The intersection is 1 point, which is the maximum likelihood estimate p hat for the model. Right. This is like a miracle. Right? This works out. So why is this true? So we want to use this idea of entropy. Is the only way that I know how to prove this theorem. So we say, okay, take the point in this PA, which is the maximum entropy. So what is the entropy of probability distribution? Just the definition. H is the letter typically used for entropy. It's the sum from I equals 1 up to m pi log pi. Okay. If I used log base 2, this is like the number of bits required to encode one symbol in this distribution. So in some sense, the unit of entropy is bits. Or if you use log base e, it's a slightly different interpretation. But you can think of it as that. How much information is it? So this function is strictly concave. H of lambda p plus, I apologize for my multiple uses of lambda to mean different things. This is just a lambda, which is just the parameter and the number between 0 and 1. So it's strictly concave. That's greater than lambda h of p plus 1 minus lambda h of q. So I'm giving two probability distributions. The entropy of their mixture is greater than the entropy of either. It's maximized at the uniform distribution. And it's Hessian. Remember, when things go wrong, our Hessian's is causing the problem. Or its Hessian is diagonal. It's a matrix of second derivatives. And it's just minus 1 over P1 minus 1 over Pm. And so the claim is that this entropy function attains its maximum uniquely. Okay, so because of the Hessian and concavity, it's a concave function on a convex polytope has a unique maximum in this set of feasible distributions. And I'll spare you, I mean, you can just run through the calculation, but the idea is that considering, so you just do a little bit of calculus and it pops out, basically, but let me tell you the basic idea. Considering the directional derivatives, it turns out that the vector of log probabilities, so this is, I have my matrix A, and I have a probability distribution on the top that I'm interested in that should somehow come from the matrix. And I can take the log of that. That's what the log of it is what's going to come from the matrix, because each column represented like a monomial once I exponentiated it. So the log probabilities is in the row span of A. And we just pick a lambda star such that I get it. So I should think of my lambdas as being weights. I have this matrix A. My lambdas are weights. It tells me how to add up the rows in order to get this vector of log probabilities, i.e. lambda star A is equal to log P star. And so these things are our NLE coefficients. And the thetas, the multiplicative versions, are just the exponentials of this. And then you can show that this point is not only a solution, but is a unique solution, again, by considering the entropy. If I have two solutions, then you can show that they're the same. Okay. So the story is that this is for your understanding, obviously not for calculation, but the story of these types of models is that you can think of them as simply matching all of the sufficient statistics, matching all of the terms that you choose to include in the model, matching all those terms exactly among all the probability distributions that succeed in doing that. It chooses the one that maximizes ignorance. And that is the maximum likelihood estimate. Any questions about that before the next thing?
Yeah, one good question just for the clarification. So I was wondering, the theory we are using here, whether we are trying to say the cell probability is just kind of stabilized. If we just using the cells count divided by the total number of
Right. So in this case, we're thinking about the multinomial model. We're not trying to estimate the global Poisson rate. So what I've said here, I think you can adapt it to that situation. But what I've said here is entirely about the multinomial model. So in other words, what I'm saying is that the lambda parameter is there, the single lambda in the front is there, but it's not interesting. It's not part of our experiment. So it's allowed to fit such that what I get out is probabilities that sum to 1. All right, fit it and discard it, kind of, yeah, because I'm only interested in the probability distribution, the multinomial probability distribution rather than the Poisson distribution. Okay. So let me now dig in a little bit more to the examples. So the example that you have in your notes, which is in section 10, about the graduate admissions example. Okay, so this was our graduate admissions at Berkeley, and we had department, which was A through F. We had gender, which is male, female, and we had accepted, yes, no. We were trying to figure out whether there was bias, and this is an interesting case because it illustrates this, but it also was litigated, and it's interesting because it was one of the few examples where the court had to actually think about which model fit best. So that the court had to decide whether it thought Simpson's paradox was going on or not in order to decide the case. I won't fill in the whole table, but it's got cells like department A, men rejected, men accepted, 313, 512, et cetera. It's that table. So we're going to look at a bunch of different models for it and think about how they fit and which one we should choose. So the biggest one we could choose would be the saturated, and what they mean, of course. So we're interested in modeling the cell counts, Uijk, the global total times this probability distribution, Ijk. Right? And because we can always do this factorization is one reason this last discussion could focus on these probability distributions and not on the global, and not on the counts explicitly. So in the saturated model, we have a term for the global count. We have terms for each of the marginals. Let's make these T, S, A. We have terms for each of the two-way interactions. And we have a three-way interaction term. And if we got rid of that, it would be the homogeneous association model. So we have sort of a grand mean, we have main effects, Although really these are not so much the if I didn't estimate this, these would be kind of main effects. When I do estimate the higher order interactions, I shouldn't think of these really as main effects, but kind of the leftover main effect after I take into account all the interaction stuff. These are the interaction between two variables while controlling the third. So these things correspond to conditional odds ratios. And this is the interaction from the three variables. So what's the biggest term or the minimal sufficient statistic in this model? Sort of a silly question. It's just this, right? It's the whole thing. And that's where we sort of have to focus the interpretation. If I asked you what the model fit statistics would be, this is the one where you can tell me the answer. The likelihood ratio g squared is going to be 0 on 0 degrees of freedom. So okay, great, it fits. Let's see what else. I could look at coefficients, like if I look at the lambda SA JK coefficient, and the coding depends on the software, but let's say this is department F and female are the reference ones, the zeros. So this lambda SAJK corresponds to the partial table department F, reject, accept, men, women, 351, 22, 317, 24. So in other words, when we estimate this, we'll get 0.1889. The exp of 0.1889, or 1.208, is equal to the odds ratio from this table, 351 times 24 over 317 times 22. So it's, part of the point of the homework, of course, is to get a little bit of practice unpacking these things. So you ask if you do one of these models, and then you should be able to figure out where each of the coefficients could come from, or what they represent, like what odds ratio or what change of odds ratio they represent. And it's usually a little bit tricky to do that. And one of the things that makes it tricky is that depending on which package you use in R, whether you use R, SAS, the baselines will change and different things will change, right? So you have to be careful that what it's doing what you think it's doing. We could get, Z statistics, chi-squared statistics, and so on for this. The p-value, if you did that, is about 0.53, so it's not a great coefficient, not significant, but you have to interpret that in the context of the rest of the model, which is a big model. So. And if we wanted to get the SA ratio for a different model, or for a different department, we would need to combine that with one of the interaction terms. So let's see, 0.86. So let's say if I wanted this odds ratio for sex and admit with the department equal to department A instead of F. This would be well, okay, it's X of 0.1889, which is that one, plus 0.8632. And this 8632 is actually one of the entries of the LDSA. Right, because we've changed department and we have a three-way interaction term, so we have to look at this term to understand how this ratio changes. Right? If I have no three-way interaction term, that's assuming that these are all the same, no matter what department I'm in. If I do have this term, I have to add the appropriate entry from this that reflects the difference between A and F. So that's kind of painful, but that's how it is. And we can go through the other models. Maybe I'll just, since we don't have much time, let me just skip to the end instead of talking about each of the models. The summary table. Summary table, once you fit all the models, will look like this. DSA, full independence model, 16 degrees of freedom, G squared is 2097, p-value less than 0.001. DSA 11, 876.6. DSSA 10, 782. And DSDASA 5, 20. Okay, so this is sort of interesting because none of the models really fit. Right? So according to our usual criteria, everything except for saturated, the fit is poor. And so this is a situation where you kind of have to decide to take the least, this one is like the less of the evils, right? So this one fits, but it doesn't fit, but it doesn't fit. Its failure to fit is not as spectacular as the others, right? So the others are all like, doesn't even come close to fit. This one is, well, sort of okay. I mean, not great, but better compared to these, which are just not even close. And you can do that question formally by looking at the delta G squared here. And saying, well, okay, this delta G squared, there's about a 760 change in G squared, and that's only on 5 degrees of freedom. So certainly we can say that the gain that we get from adding the homogeneous association term, the dA term, that makes this model go from conditional independence model to a homogeneous association model, that gain is highly significant. The other thing, of course, we could do, as we learned a couple of classes ago, is to throw at this a AIC-BIC type strategy, and I think that would almost certainly choose that same model, the DSDA SA model.
So the log linear is a bad model for data?
Yeah, I guess maybe it is. Or I mean, another way of saying it is that the model just doesn't really fit very well, and it could be that there's, I don't know, some other piece of missing information, like how good the application was or something. I mean, that's sort of, it would be, that's not surprising in some sense, right? Like there should be some variation, a lot of variation left over. We wouldn't expect that those three things would predict acceptance. right? They maybe wouldn't need an admission. They wouldn't need GREs if, if all of these things was enough, right? So maybe in some sense, you could think about there being over dispersion caused by the fact that you're not modeling the quality of the applicant. Anyway, so I might talk about it next time in more detail, but it would be crazy to do it now. But if you should look through this example, especially as you look into the homework for next week, which is on more log linear modeling, doing an example like this one. It's not so different from the things we've already done in terms of comparing different. The trick is mainly in this kind of when you have a lot of terms, figuring out what the correct interpretation is a little bit challenging. Otherwise, it should be all right. Okay, so I'll stop there. If anyone has questions, please join me.